So to begin with, Pat, can you tell us who you are and a bit about your background and the path that led you working with NASA projects, and of course, what projects you work on?
Yeah, so I came to NASA, or started working with NASA projects in 1988, came to Goddard in 89, and then became a civil servant in 1990. So I've been here a while, seen a lot of changes. I'm an electronic engineer, specifically electronic instrumentation engineer, and now more like an electronic instrument systems engineer, which means I kind of have my hand in all aspects of instrument development, which is awesome. And Stella is an instrument, so it kind of works out well, just a little more on the education side. But I do have a background in instrument design development and things like that as an engineer.
So you said you were an electrical systems engineer and an electrical instrument engineer,
Yeah, so
right?
I guess
What's the difference between the
so
two?
technically I'm an electronic engineer, not
Electronic.
electrical.
Okay.
If people want to know the difference between that, in general, there's a lot of overlap, of course. Electrical engineers are really thought to be more with power systems and distribution and what you would say less intricate, larger systems, where electronic, we're dealing with like the microcircuits, transistors, things like that a little more. Of course, there's huge overlap anymore, and it's hard to distinguish between the two. But they do still have electrical and electronic engineering degrees. So I'm an electronic engineer by degree. And then when I came to Goddard specifically to work on scientific instruments, you could say my role here is an electronic instrumentation or instrument engineer, and eventually an instrument systems engineer because I became more familiar with disciplines outside of electronics. You know, the thermal, the power, thermal, vacuum systems. Uh, um, what other kind of aspects are there? Yeah, mechanical engineering, all those things I got involved with as an instrument systems engineer, especially small projects. So I've been used, and I work in the science directorate, not with in the engineering directorate. So I work directly with the scientists when we try to conceive and collaborate and try to come up with new applications to do scientific investigations based on opportunities. In other words, money to do stuff. And they come in and say, hey, this is whole thing we wanted to study. Particularly, my career's mostly been with the sun, although I have worked with astrophysics also, um, where they decide, hey, there's something we want to look into, or we want to improve upon this type of instrument to discover, get better data. They work with me, and we conceive of it at the beginning level. And then when it becomes a large mission, that would be handed off to a larger team of engineers. Or if it's a small instrument, particularly CubeSats or most of my career, sounding rockets, which are suborbital rockets, I would have my hand the entire way, right out to being out in the field, recovering them when they come down on a parachute, riding out in a helicopter. So yeah, mainly done early on are small missions, which allows me to have my hands through the whole process, which I like. Now, the downside is we usually have very little money, not as much time, but that makes me very, I would say, resourceful, having to learn how to do things on the cheap, which I love. Hey, mom and dad grew up in the Depression, so I was taught that way. So I feel like that's been my main contribution here at NASA, is learning how to do things when you don't have many resources.
How did you first become involved with the Helio-STELLA project? What was the initial vision that you were thinking for Helio-STELLA, and how did it evolve during the development process?
Sure. So several years ago, I very luckily fell into, because someone recognized my interest and enthusiasm, uh, into what was called NSEC, the National Space Education Consortium, which then turned into HEAT, more specifically Heliophysics Education Activation Team. So it was more of an educational side and outreach, somewhat mostly educational, for getting heliophysics out there into the community with educators, scientists, and an engineer, me. Paul Morell was also involved before HEAT, so I knew him. We collaborated and worked together in the lab. He was my mentor on several things. Sometimes I got to teach him something that he didn't know, but mostly it was the other way around. Brilliant, innovative, resourceful gentleman, which I always respect because that's where I come from. And I had seen him working on Stella in one of our labs here in the building, the STEM Innovation Lab, which I was loosely involved with at the time. And then moved down the road maybe a year or two, we have an event here called the Goddard on the Green, uh, which is kind of where a lot of organizations at Goddard display what they're doing. You know, some of it is more science, education, engineering, some of it's food, some of it's the clubs. And then you came wheeling in a pulling a wheel, not a wheelbarrow, but a wagon of Stellas. And I go, hey, that looks familiar. And that looks really cool. And we got to talking and we're all excited and saying, hey, we should collaborate. And I said, yeah, let's do a heliophysics Stella. And we got together, you and I, and we brainstormed. And I said, hey, it would be really good if we could have a Stella that was heliophysics focused in time for the big eclipse coming around that year, the big total solar eclipse in April of 2024. And we got together and we went to Michael Kirk, who's the PI on HEAT, and we had to sell it to him a little bit, but he said, yeah, that's a great idea, let's do it. And Paul Morell made it happen. He's the engineer and software programmer, and he came up with a fantastic device in time for us to give out kits for people to build, for us to build, and for us to have spread out across the path of totality across the U.S. In various locations to actually promote and actually measure the sun's behavior during the eclipse, which was a great promotional, but also scientifically it was very interesting. And I was very thrilled and happy with it, as I think everyone else was. But hats off to Paul for doing all the real work. I just kind of came up with the idea and got in the middle. As Paul likes to call me, he calls me the application engineer. I call myself the salesman, but I do promote the heck out of it. And everywhere I show people, they get really, really excited about it, primarily due to the cost, especially with educators. It's so inexpensive, and that was our primary focus on it. That may be another question you have later, but we can come back to that. But that's how it all started, and let's do it in time for the eclipse, and we did.
Alana Resnick was also with us, and
Yep,
right, and there was some contribution. I think it was the four of us
yeah,
talking
absolutely.
about the Helio-STELLA together. So that was
Alana's from the education side. She was able to kind of give us that pull. I was just kind of an excited engineer. Paul was the experienced, and you're the guy who thought of the whole thing and manages all of Stella. Fantastic. Just so glad we're able to connect, because it's perfect, and it's the kind of stuff I love doing, and I can do it. And I'm just really grateful that all the timing worked out perfectly. And I think from where I stand, it's a huge success, and it's not done. I think there's a lot of things we can still do with it.
So how does your work on Stella/Helio-STELLA connect to other engineering projects you've been involved with? And obviously you mentioned low cost, so go ahead and continue with your train of thought.
Yeah, so absolutely low cost it gives me good position to help develop this. Often we have to prototype things in the lab with just things I have laying around, or I can borrow, or things that don't cost too much. And of course, the Arduino Raspberry Pi world has already been well established and laid around, and so that just seemed like a natural fit. And of course, we'll get back into this. Stella has already been making use of those for a while now, and that gives it accessibility to education. But again, we'll get into that. But as far as my experience specifically, most of my career has been with heliophysics, studying the sun and the sun's effects on the Earth. And Helio-STELLA was aimed at that. So in particular, most of my instruments I've designed are imaging spectrographs, so looking at spectra. And for people who aren't in the scientific community, when you're doing remote sensing, like looking at the sun or stars in astronomy, most of the information is in spectra, not in a picture. A picture is pretty, but it basically gives you 2 dimensions versus intensity, made in whatever kind of light or wavelength region you're looking. But when you look at the spectra, in other words, spread it out into a rainbow, that's where really most of the information is. You get to see what each energy level are. So from that, and I'm not a scientist, I'm an engineer, so bear with me. When you spread it out and see all the energies or intensities at the various wavelengths or colors, that allows you to figure out through some processing what that star or sun is made out of, how fast it's moving, what temperature it is, and that gives you a lot more information where we can come up and theorize just what the heck's going on in a star, particularly ours. And I will tell you, from where I sit, we still have a lot to learn, which is exciting. We're still learning all the time about what's going on with our sun and how it affects us here on Earth.
Okay. Can you walk us through some of the engineering challenges you face creating an affordable, accessible, heliophysics or just instrument itself that can deliver actual meaningful scientific data?
So luckily, the challenges were very minimal in this case, due to the fact that the Stella program already existed, and the majority of the instruments that we came up with for Stella had already been developed. The software was developed, the instruments were already integrated, which is basically an 8-channel spectrometer that measures white light um, um, intensity, and I think eight channels of visible light. That would already been implemented and tested in the software to develop. So when we sat down and thought, all I suggested was for an inexpensive, useful um, heliophysics centered Stella was to add a UV sensor. And so really, all it was really needed was to add the UV sensor and trim down the software maybe that was already there for the other Stellus instrument suites. So the only real challenge was time, right? We had the eclipse coming up and wanted to get it out there beforehand so people could go ahead and build one. So, and again, that is an engineering challenge. There's not just the, you could say, physics challenges of engineering. There's the time and money challenge. So in this case, money wasn't so bad because we came up with one that's pretty inexpensive, but it was time. And again, Paul Morrell was able to develop all that in record time, and it worked great. But so as an engineer, and which is probably true outside of engineering, one of the real advantages, and if I can use a management term, we leveraged all the work and effort developed that had already been done with Stella to just make a modified and in all honesty, a simplified version with an additional detector, the UVA sensor. So it was great, efficient use, I think, of what already been done and not having to reinvent the wheel, if you will.
When the collaboration between engineers and educators seems to have been crucial to basically the Stella's development, of course, as well. Could you share some examples of how this cross collaboration worked in practice?
Sure. So as opposed to being, I guess I don't know how to, it wasn't like a time synchronous collaboration. It was more like my exposure and Paul's exposure previously with educators. We kind of already knew what kind of our goals would be. I think I did speak to a few people about what they would think, but I think Paul and I already knew, and you did already knew what this was going to be like. And the main thing was accessibility, which part of that is cost. How we, you know, where can we get the parts? How much does it cost? And then one of the plans per the PI here was for us to actually buy enough parts for 20 kits to give them out and distribute them to folks. So all they had to do was put them together. So it was also a fun project kit to build, which I think, in my opinion, 5th grade all the way up to college, absolutely. The Stella, particularly the Helio-STELLA I'm more familiar with, really had a wide range of potential students, whether the students were also the educators or not, where it was easy to build all the way up to whether you're doing higher level experiments or even modifying it at the high school or college level. It really hit a wide audience, I think. And so like a lot of the collaboration was really from previous knowledge. And we did speak to some educators a little bit to confirm it, but we were right on track from the beginning, I think. Mainly accessibility, which, like I said, is cost. The most rewarding thing to me is when we would go to these um, events like the promoting the eclipse, where we had teacher workshops where we were teaching teachers how to teach heliophysics. I was promoting the new Stella, and as part of that, they'd come by and I'd show them, and they'd go, "What is this?" And when I told them how much it cost, their eyes lit up, right? I mean, because teachers today, sometimes they have to buy the stuff with their own money to get what they need in the classroom, and that this thing at the, less than $100. Last I checked, which was probably 5 months ago, if you already had a USB cable or connector and a micro SD card to log this, all the parts online, commercial, $83 to build one of these. So it may be a little more now, but to me that is awesome. And again, that's what I think the biggest collaboration with teachers was the accessibility. Now, what it actually teaches is fairly simple, but it's at entry level, it teaches and demonstrates at whatever age you are what spectroscopy is. Like I mentioned earlier, a lot of people, they know what the rainbow is, but they don't realize from a scientific standpoint, you know, what that really is. You're actually spreading out and looking at all the relative intensities of all the colors and demonstrating that in the form of a data set that can be graphed or analyzed very easily from this data set, which is recorded, so that you can do scientific analysis or experimentation to whatever level that student or teacher is working at.
How do you see Helio-STELLA helping to develop engineering and technical skills in students who might become the next generation workforce?
Okay, that's a good question. Um, as an engineer and who felt really lucky with the engineering school I went to, which was very hands-on, often in engineering at least, um, uh, a lot of educational institutions, and maybe it's different now, were really heavy on the fundamentals and theory, which is very important. And then they would expect that most people would learn the practical side on the job. Well, in an environment here at NASA where we want to kind of be in the lab developing and building stuff right off the bat, um, my school was pretty good that way, and that we had a lot of hands-on in-lab experience. And so many of the students, all their experience was in the classroom and tests. They never really had to build something from scratch. There would be maybe some lab experiments, but all the parts were already found, bought, tested. They already knew it worked. And so what this, besides the science and the application of like the Helio-STELLA, it would teach students another part of engineering which they may not get in most education, and that is, where do you get the parts? How much do they cost? How long does it take to get them? And then hooking it all up together and making it work. That's something that this Stella could very, very well teach, and at a low cost that may not be readily available in any existing curriculum.
Could you explain some of the key technical features of Helio-STELLA and how they relate to professional instruments used in the field?
Okay, so again, I'm not a scientist, but Helio-STELLA is a basic demonstration of spectroscopy. You know, it's got a spectrometer in there which looks at 8 wavelengths of visible light, has a white light meter, um, and then we also added a UVA sensor that measures what's called near ultraviolet UVA. Um, so what that allows them to do is look at spectra at the ground level, which honestly in heliophysics we don't do that as much. We really want to get out of the atmosphere to look at you know, extreme ultraviolet out in the vacuum, because the Earth's atmosphere blocks most of that. However, some of it gets down here, but it does demonstrate spectroscopy at a level that is actually useful, especially during eclipses. How does this light get scattered? What lights are absorbed? You know, what light is coming through the atmosphere that's not directly coming through us from the sun, that is normally blocked during an eclipse. So it was very useful to use this during the eclipse, where scientists would be doing real high-level science during the eclipse, and we were able to see that the Helio-STELLA was actually acting very much like higher-end, more expensive, more precise scientific instruments. So the Helio-STELLA is definitely, you could say, depending on your opinion as a scientist, can fall into the realm of citizen science, where it's actually useful data, to actually some real science. Again, the real expensive instruments go on spacecraft and things like that, but that doesn't mean that this is not useful. So one of the parameters in science is, when you propose to do work, is you have to do something new. It's like, okay, we haven't done this before. This instrument's either better in some ways. It's more sensitive, it has more resolution, blah, 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 has higher performance, less noise. Well, what the Stellas can do, as you know, can give you more geographical resolution. We can have a whole bunch of them all over the place across the Earth for low cost, and that is a form of resolution, and that's like the basis of a lot of citizen science.
Fantastic, man. That's
Yeah, yeah, and so it is useful, and it demonstrates in line exactly what a lot of scientific instruments do. It's just a low-cost version of it, you know. Also, in particular, the data sets. How does it gets the data, but it also logs it in this case, a spreadsheet, which pretty much anybody can import, you know, look at on a computer and graph and do analysis on it with a spreadsheet program. That is key in scientific instruments. You can measure the data with the instrument, but what are you doing with it? And so the Helio-STELLA is storing it automatically on an SD card, and then in an easy format for people to exchange, look at, and manipulate. That is a part of science a lot of people aren't familiar with, and Helio-STELLA does a great job of that.
I understand that UV detection capability is particularly valuable. Could you explain why this feature was important to include and how it works?
Yeah, so the idea of adding the UV sensor to this was because the original Stellas did not have that. They already had the spectrograph. You guys have already built on that. I go, how can we make this? What else is there we can see on the surface of the Earth? And I go, well, we can look at ultraviolet because that's really key from the sun. Ultraviolet light, uh, drives so much here. It damages plastics, breaks things down. There's health issues with UV. I mean, we need some UV light to be healthy, but too much, of course, we know is bad. So the UVA sensor added, another capability to this without too much cost, and it allowed us to monitor. Well, how does the sun's UV output vary with, cloud cover, eclipses, whatnot? From different directions. I also thought of things like, well, we always hear about, oh, you need to wear UV blocking sunglasses or windshields. I go, well, hey, we can kind of measure it. Now, it's not a precise measurement that's going to guarantee you'll never get skin cancer, but it does demonstrate relative performance or blocking of different substances. And right now, collaborating with Carroll Community College, their electronic engineering department, they built a Stella, they're excited, and they're collaborating with the physics department to actually do some experiments. So Paul has already added the software to this. If you just spend $15, you can replace the UVA sensor with the UVA, UVB, and UVC sensor. It's more expensive. We didn't put that in the original. It's going to cost you another $15, which put us over the $100. But you can definitely make it that. And they're doing that at the community college to actually do experiments, putting different sunscreens on a substrate to see just how well, relatively, these different sunscreens can block UVA, UV, and UVC light, which definitely affects skin cancer and sunburn and aging. So again, it's not a calibrated medical instrument, but it does demonstrate relative performance of different substances to block those wavelengths. And I think that's really awesome because as an example, when I was still excited about this, I still am, can't you tell? Years ago, I took one to the beach on my family vacation. We're all sitting around and a thin layer of clouds came over. And of course, the age-old myth or misinformation where people said, oh, thin layer of clouds, you get sunburn worse with that. And I was like, no, you get misled thinking there is no UV light because it's cooler, it's not as dark. There is still some UV light. So a lot of people get burned during those because they think they're not getting it, but it absolutely is less UV light. And I said, well, why are we arguing? I ran inside and got one, and we turned it on and we watched it in real time. We watched the UV light go up and down as the cloud cover came by. So we were able to prove that yes, even the thinnest clouds reduce the amount of UVA light. So so that was great. So you don't have to argue or wonder or go trust a Google search. You can demonstrate it with your own instrument.
Could you envision an integrated system where multiple Stella instruments work together to provide a more comprehensive data set? What engineering challenges would that represent or present?
All right, so different ones of the same configuration or different Stellas connected together?
Different Stellas, so if you were to design another Stella, something
Okay,
that would complement the heliophysics Stella,
okay.
and all that, or as well as maybe enhance it as well. What would you put on there? What would you be thinking about? How would you come up with it? What would be the constraints and all that sort of stuff?
Right, so we've already worked on that. Paul, again, has already done a version 2, if you will, that incorporates the only other things we really think could be demonstrative of heliophysics, and that is a 3-axis magnetometer and a GPS device. So Unfortunately, magnetometry on the surface of the Earth isn't quite as precise to predict or demonstrate the sun's behavior, but it can in certain cases during solar storms. And it still demonstrates some things. It's not quite as sensitive, but it can, all in one package, show you magnetospheric variation along with any photometric, that means light variation, the UVA, B, and C, uh, ultraviolet light, the visible light, magnetic fields, and then with the GPS you could time tag and show exactly where you were and what time it was, so that you could register that with all kinds of other data, which we did with some data NOAA took during a solar storm. I think I can't remember what year that was. I think it was 2024. But in one of our papers, as you saw, we were able to prove that the Helio-STELLA kind of tracked some solar storm data pretty well, not with the resolution of multi-million-dollar instruments, but it showed that it works. And so to me, that's really citizen science, and showing that this thing is actually showing real data, just not with the resolution of a much more expensive, inaccessible instrument. But again, that's kind of, from what I understand, what citizen science could be, in that instead of having something that's very, very sensitive, we have something where we have a whole bunch of them all over the planet, which we can do. And because it's inexpensive, you could have all kinds of clubs, schools, everybody, and they have done that before with magnetometers, but not with the Helio-STELLA. But we can definitely do that with the Helio-STELLA in the future. And again, link it up with other Stellas and their instrument suites, or we can make the modularity where people are kind of inventing and building their own pretty easily to fit their educational or our citizen science needs.
How do you think basically that stepping stone can happen with, say, the Helio-STELLA? To get up to, starting to understand some of the actual professional instruments, and then why,
Yes.
and then explaining how or why we need, say, those professional instruments, those big, say, heliophysics
Okay.
projects and all that. How can it be a stepping stone to do that?
Okay, so that's a good question. I'm not being a scientist. I can tell you just from experience, seeing and building instruments, that in the case of heliophysics, um, Helio-STELLA, like I said, measures light in different wavelengths, including UV light, and magnetometry is something else that's done in the case of expensive instruments out on spacecraft. Once you're outside of the Earth's atmosphere, you can see a lot more light, particularly UV light, which is almost completely blocked by our atmosphere. And also we can get away from the Earth's magnetic field to as we get closer to the sun, we can see its magnetic field, or our magnetic field farther away, which is more influenced obviously by the Earth's solar wind and things like that. And so Helio-STELLA is like one of those, just like I said, a much more inexpensive and lesser performing. But as far as a stepping stone of like instrument development, it's very similar. Now, like been going on for years, is money's tighter. You don't have as much opportunities as you had back in the day. Maybe that'll change with these huge, very expensive 10, 20, 30-year-old development time projects like Hubble and the Next Generation Telescope. You have to come up with ways of building smaller, more inexpensive ones, and that's exactly what this is. And in fact, some of the electronics that is used in Stella, we have put on actual satellites. We really have. So what I've learned doing Stella, and other people have learned doing Stella type educational projects, are absolutely transferable to real scientific instruments, although they may be beefed up, or maybe some other instruments or detectors to give it a little bit more resolution for performance per se. But there's some overlap. It's not just like a toy. It really is not just a toy. It's really showing you how scientific instruments work and the challenges to develop them are. I think it's real. So it's a great education, science demonstration, and a citizen science tool that is accessible, both cost and availability. Sorry, I'm back on my sales pitch, but it's true. I truly believe it.
What are your hopes for the future of Helio-STELLA and its impact on STEM education?
Yeah, so I have to say my experience, which is limited in some way, everywhere I go, where there's educators or people who are sort of interested in like this, where it's educational conference or it's a real scientific conference. When I show this to people, the reaction is always great. Everyone loves it. They want one. They're going to build one. Where do I find out about it? Everybody seems to be really, really excited about it. So that being the sense, I think there's still a long way to go out there. And to me, the biggest challenge is letting people know about it. I think the more people we can reach, the more it'll be used, the more it'll be built, the more it'll be applied. And of course, we haven't touched on that, but the modularity and easily modifiable architecture of this will allow people to custom build their own very easily. And my aspirations in the future is not what I want to do, but what all these other people who are educators and know better than I, what needs, what educational gaps and scientific gaps, citizen science, need to be filled. And so my excitement is, and my goal is I need to get the word out more. And we're doing this right now. It's great. And the more people we can show this to, I think we don't know where it's going to go. But me particular, the next generation Helio-STELLA, again, is like almost already built with a 3-axis magnetometer, a GPS sensor. It already has the timestamp showing the data. But what I would also like to add is something which would be basically another board that you could just buy online. That's a 4-channel voltage measure, also known as an analog to digital converter. And once you put in the software for that to actually just measure a voltage out on some lines, you, as the owner, user, educator, tinker, whatever, you can build your own detector that can detect anything you want and just convert it to a voltage. And this thing will log it and put it in a spreadsheet for you. You don't need to change the software on this. And I already know there's a scientist here, one of our big, way smarter than me scientists. She already has plans to make a muon detector for this. And that's just, I mean, so I think really the sky's the limit when we put an A to D converter on this, A to D converter board. And then people can build their own detectors, detecting whatever they want. And I know in one of our papers, I was thinking, okay, if someone wants to do experiments or monitor their solar power system, they could just measure the output of the solar power system, whether it's for fun, for education, for their home, their business, against what the sun's doing, and see just how efficient it is. And then you can optimize your system based on cloud cover storms, which colors are better than others, which produces more power when the sun's more red versus a violet or indigo. Those kind of things. It's just the sky's the limit, I think. And that's what I'm the most excited about, because I think once we add that, it's only limited to people's imagination.
So, what advice would you give to educators who are using Helio-STELLAs to prepare students for future careers in STEM?
That's a good question. I think in the case of Helio-STELLA, like other projects, actually having to build something and maybe even obtain the parts, buy them, find them, put it all together, make it work, is absolutely a great part of STEM education, particularly if you are going into engineering or even science, because it goes beyond what it says in the textbook, and you get real world challenges. Things don't always work right. I plugged it in wrong. Now did I destroy it? Let's test it, make sure, do I have to buy another one? Those things you can only really learn by hands-on experience. And so I think having Stellas are things like Stellas where the students actually have to put it together, program it, and make it work is a great lesson in STEM education, particularly the E part, the engineering part. And the T, right? Technology, is that it? Yeah, science, technology? I forget, yeah. So this definitely hits all of those.